This is Signal Hound's Talkin' RF, and today we're talking how to adapt one of Signal Hound's API examples to build a custom RF measurement solution.
This is Signal Hound's Talkin' RF. Sean here, and in this video I'm going to show you how to adapt one of Signal Hound's SDK examples to build a custom RF measurement solution tailored to your exact needs. Whether you're working on spectrum analysis, signal detection, interference monitoring, or integrating RF measurements into a larger system, Signal Hound's API provides the flexibility and control you need. I'm going to walk you through how to configure custom measurement parameters and process the results of an on-off key signal, all with C++. This approach empowers you to create scalable, reusable, and tailored RF workflows that can be run unattended and integrated with your application or extended to new features. Let's start exploring how to unlock the full potential of Signal Hound's API for your unique use case.
For this demonstration, I'm using a BB60D and an OOK transmitter. We need to start with the information from the transmitter. We don't really know what the baud rate is for this device. Let's look at it in Spike, and then we can determine what the baud rate is. We can then use that in our example. In this example, we're going to hard code the sample rate. This transmitter operates at 315 MHz. To get started, go to zero span mode with a 10 millisecond sweep, with the video trigger rising edge at -30 dB. Let's take a measurement. This is a 1 and a 0 for the on-off key, and now we will add a delta marker. Here we have about 292.85 microseconds. So let's get the calculator out and divide 1 by 292.85 microseconds. That will tell you that the baud rate is 3.4K. We will operate at that rate. We're going to create a new Visual Studio project. For now, we will close Spike and remember that our baud rate is 3.4K. It is important to write that down and to remember that number. Next, create a console app. Create a project for the BB60D OOK DMod, and with the SDK downloaded, go into Device APIs, BB Series, and Examples. We will be working for the video trigger example. I'm going to take the video trigger example and copy it. Then I'm going to use the BB60D OOK DMod to drop it in the C++ files. Then, pull in the header, the DLL, and the library files for the BB API that are all in the BB Series folder. The headers in the include. The lib and the DLL are here in the lib, win, Visual Studio 2019 x64. As you can see, we also have the FTD2XX DLL. This is the DLL for our USB interface. Copy the BB API as well as the header and put these right here in the Visual Studio project. Add an existing item to the example and the header. We're going to use this as the function and add the function to process the data. Call that in here from the main, and we'll call this the function. We have to define and make sure everything builds. With everything built, let's run it. This is the video trigger example. I will inject signals to get it to complete. With the function created, I want to process the on-off keying data. We've modified the center frequency to listen at 315 MHz. And copied over code that I wrote earlier with a functioning OOK DMod. That needs to be able to correlate the sample rate of the BB60D and the baud rate of the transmitter. Here is the OOK DMod function. First thing that I want to do is take the IQ data and calculate the amplitude from that. That's what we've done here with this equation. 10 times the log base of the imaginary data squared plus the real data squared. We measured the baud rate at 3400 in Spike. From that, we want to take the BB sample rate and divide that by the baud rate, which is the samples per symbol. Because we are dealing with such small fractional values, and we don't want that to cause the center point to wander, I made these values doubles to mitigate the chance of that happening. With many data points, you could eventually end up taking your sample rate in the wrong spot. To calculate the exact center of the symbol, use samples per symbol divided by 2, because we triggered at the rising edge and we want the symbol center to be 1/2 of the samples per symbol from that point. You are trying to land where you take the sample. Then collect the data at the exact center of the on or off point in the on-off keying. We've got a bits vector, and those just aren't ones and zeros. I used int8s as a small data type for capturing the ones and zeros. Look at the amplitude at the symbol center rounded down, and check that it is greater than -40 dBm. If it is a 1, or if it's not, then it's a 0. Then shift the symbol center by samples per symbol. Move over to the center of the next sample point, and that's the OOK demod function written to extract the data from this OOK transmitter. Save it and build it. The video trigger example does IQ streaming only. It looks at all the data points to see if the threshold has been crossed for an observed signal. That is how we look for the data without a trigger signal being fed into the BB60D. Look for it in the actual data. With the rebuild complete, let's run it. It ran and sensed it. It wouldn't have gotten there if it didn't sense the signal.
Today we explored how to use Signal Hound's API to create custom RF measurement solutions tailored to your needs. If you have any questions, please contact us at support@signalhound.com or leave your question in the comment section below. Like, follow, and subscribe for more Signal Hound and RF content.